I think this is the first time that you see double here. I think they fixed it or something, which is time and good news. So now you don't have to sit on this side. You can sit anywhere. Okay, so the main announcement is that you have homework 4 out. I know that many of you already know about it. And as I always say, please don't wait until the last minute or not even the last day, because it's going to take some time. I think it's a nice problem set, so hopefully you will enjoy it also. Any questions? Yeah. 14? 14. And today is the 5th, so 9 days, yeah. Yes?
I just want to confirm that after today's lecture, we'll have learned everything.
Yes. In fact, you've already learned everything after the previous one, except for the extra credit, maybe, after Tuesday. But I'm going to discuss a little bit some of the issues today, especially if you have questions. Okay, so let's start. So we are talking about Bayesian learning, and specifically we talked last time about naive Bayes, and I want to recap because it's going to give us a good introduction to what we're going to talk about today. So this is naive Bayes. The Boolean case where we want to make, we have 2 options for decisions, and in this case the decisions are N or V. And essentially what we do is we collect probabilities given N, and then we collect probabilities given V and compare. So we can figure out what is, using Bayes' rule, once we have these probabilities, we can compute P of N given X and P of V given X. But again, what we estimate is the P of N and P of V, which are the priors, and the P of Xi given N, which is how we decomposed the X x1 up to xn, but then when we use Bayes' rule, this gives us the probability for each one of the labels. Now, the question that I asked you last time was, we know how to do naive Bayes, but it so happened that we only have 10 examples. So we learn a model from 10 examples, and that's what we got. But then suddenly someone tells us, you see, you have 100 more examples that are unlabeled. How would you use them? It would be a waste, because they don't have labels, to not use them, because you could assume that they come from the same distribution, that the 10 example came from, so there is some information there. And we discussed this a little bit last time, and we kind of converged to a couple of approaches. We realized that we can take each one of these examples and run the model that we learn on the 10 examples on them, and then it will give us some predictions. So option 1 would be to make these predictions and believe them, annotate the data, the 100 examples with them, and use it. That could be a solution, but maybe not the ideal solution. So another solution that we suggested was to fractionally believe them. So really, when you say, using naive Bayes, that an example is an N example versus a V example, you not necessarily say, I know probability 1 that it's N or V, but rather you say, I know that it's N with this probability, and I know that it's V with this probability. So in principle, I can take my 100 examples. I don't need to label them N, V, but I can label them N with this number and V with this number. So every example will have 2 numbers two fractions between 0 and 1 associated with it. One is the n weight confidence, if you want, and one is the v. Why is this good? The reason is that now I can use or reuse the naive Bayes algorithm on this new data set in a slightly more conservative way. Right? So I will not just say that this example is an n example because my model based on 10 examples thought that it would predict n on it, but rather I would say this is 0.8n and 0.2v, reflecting the lack of certainty that I have, or the uncertainty that I have in this example. And I can do this for all 100 examples. So now I have predictions, and I can take my 110 examples now and run naive Bayes again on them. So how do I run naive Bayes? Again, remember, what did I do here? I basically computed P of x1 over n. What was computing P of x1 over n? It was counting how many n examples I have, putting this in the denominator, counting how many of these examples had x1 being 1, say, and this was the number I put there. Now I can still count it over the 110 examples, but I will count fractions. Okay, so this way I'm a little bit more conservative. I don't necessarily believe the algorithm. If the algorithm, for example, gives me 0.5, 0.5 for n and v, it's as if I don't count this example at all, because it contributes the same thing to both sides. If, on the other hand, it's very certain, 0.95, 0.05, that will count toward one of these labels. So that's what I mean when I say fractional examples, and that's what I want. That's one option for me to use here. And in fact, this is going to be the basis for what we're going to talk about today. So I'm going to go back to this idea of fractional labels a little bit later today. Now, in addition, this could be a basis for what we call here a semi-supervised algorithm, which is basically a family of algorithms that we proposed last time. One of them is to do what I just said, make predictions, consider the confidence, this probability of predicting n and predicting v, and use some threshold. I'm going to take only those examples of the 100 for which my confidence is greater than 0.8. Or I can take only those top 20 examples. I don't know whether any of them is going to be top 0.8 or above, but I'm going to take the top 10 sorted by this confidence. So that could be an algorithm, and then I can iterate and retrain just as I said before. Or I can actually use the fractional example, in which case I take all the 100, but I weigh them differently. So I don't take the whole example, I take 0.6 of the example toward the n and 0.4 toward the v. So this is a family of algorithms, family of semi-supervised algorithms. They are all fall under bootstrapping algorithms. And this is really the most common way today to use semi-supervised learning. And this is what you're going to do in the second experiment in the homework, right? So we suggested there, I think, two options. One of them to use a threshold. You'll have to think about how to choose a threshold. Another one is to choose the top k. You have to figure out how to choose the k. And you keep on iterating until you stop. Yeah?
So if I use fractional examples and I want to calculate the final p of n's, do I just sum up the values that I found and then divide that by the total number of...
Yeah, it's the same thing, because, again, if you think about what you did here, how did you achieve this 0.75 here? Basically, you counted how many examples had x equal 1, x1 equal 1, and you divide how many n examples had x1 equal 1, and you divided this by the number of n. Same thing, only that now, next to each example, it says it's 3/4 n examples and 1/4 v examples. So you count this example both toward the n count and toward the v counts. You count 3/4 of it toward the n side and 1/4 of it to the v side.
And this works because we're not working with integers.
Yeah, who cares whether it's an integer or no when I do this summation, right? All I need is I need to sum up some things in the numerators. And I can either sum how many times I see x1 in an example, or I can count the n example partly. And in this case, I'm going to count this also against the v example. So that's basically what you have to do in your problem set when you do when you want to use these fractions. Now, those of you that have read the homework see that the first experiment is simple naive Bayes, only that we gave you 3 versions. The first version is the simple thing, the one that I showed here and the one that we've shown previously, where essentially you just do counting, right? So we want to do text classification. So you look at each one of the labels. You have 20 labels, but it shouldn't bother you. It's exactly the same as if it was one label, because when we talked about 2 labels, we did argmax over 2. Now you're going to do argmax over 20. No difference here. And for each feature, which in this case is going to be a word, you're going to count how many times this word appears in an example that is labeled L1. How many times it's on in an example that is labeled L2 and so on. So that was the basic algorithm. And then we gave you to consider 2 other representations. One we call TF for term frequency. The other one we call TF-IDF for term frequency times inverse in document frequency. Thanks. And basically view these only as coefficients over the 1 and 0 that you had before. So we gave you the formula, but think about it. Make sure that you agree that it makes sense, that this is a way to use this. So it's really the same algorithm, only that we gave you ways to use it where the features are not Boolean, but rather real valued. Everything else is the same. Questions? Yes?
But here when you say P subscript n of x, is that the same thing as P of n given x?
Yes. Yeah.
Is there a reason why we use a subscript?
No. Just to confuse the enemies a little bit, to make sure that you're insensitive to notation, because you'll see this notation all over the map. So you get used to it. But thanks for the question. Good to ask this question, so it's clear. Okay, so now that we have semi-supervised learning, the final question that I asked was, okay, let's go back to it, is what if instead of 10 labeled examples, we start with 0 labeled examples? So the only difference is this. Now I can use this. This 1 here disappears. So tiny difference, right? And the question is, what do we do now? And it turns out that you can do the same thing. The only thing is, where would you get your initial model, right? So before, you got your initial model by running over 10 examples. Frankly, it wasn't a good model. Now, you don't even have that, so the question is, what will you do? And the answer is going to be, guess a model and do exactly what you did here. And is it going to work? If you do the extra credit, you'll see if it's going to work. Or if you just do experiment 2, we gave you 3 values instead of the 10 for experiment 2. Use 5% of the data, 30% of the data, 50% of the data, I think, you can go down from the 5% and see how this behaves. And it's going to be solid. And we'll talk about when is it solid and when it's not a little bit later today. Okay, so this algorithm, once we go down to 0, is the EM algorithm. EM stands for expectation maximization. And really, EM is a class of algorithms. It's not a single algorithm that is used to estimate the probability distribution, the target probability distribution in the presence of missing attributes, missing features. In this case, missing labels. Using it requires to make an assumption on which is the probability distribution or which is the family of probability distribution that governs the generation of the data. And it's actually sensitive to this, as we'll see at the end, and also sensitive to the starting point, this initial guess. If you guess well, it's going to converge faster. If you don't guess well, it will not. And in general, it's not going to converge to the right thing. It will converge, it's known to converge to the local maximum of the maximum likelihood function. So in practice, the way people run EM is they will initialize it multiple times and run it. And hope that in one of these, and then take the maximum, the best model they found, and hope that in one of these initialization, they actually got to a region that gives them either the global maximum or a pretty good local maximum. Okay, so what is EM? So we're going to play with we're going to run EM twice today with two separate examples, just to give you an idea of the flavor of this. And I'm going to start with this coin problem. So let's assume that I have 3 coins, and I observe a series of coin tosses that are generated with these 3 coins. Coin 0 has a probability of head alpha. Coin 1 and 2 have a probability of head P and Q. So I'm going to run 3 scenarios. Scenario 1, I'm tossing one of the coins 4 times. I observed H, H, T, H. Which coin is the more likely to produce this sequence? Well, you don't know the values of alpha, P, and Q, but you can use one sentence to convince me that you know which one it is. Someone said something? Alpha that is... Yeah, but give me a clue that you know which one it is. Yes? Yes, so the alpha or P or Q that is closer to 0.75, because here you see 0.75 for head is the best estimate you can give. So you solve this problem. Scenario 1 is easy. Scenario 2, I'm first tossing coin 0. If I get 0, if I get head, I'm tossing coin 1. Otherwise, I'm tossing coin 2. And this is what I observed. H, 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 T, T, H, T, H, T. And the way you read it is that the red one is the first coin I tossed, and the second one, and the others are what I tossed later. So now, the question again, give me the most likely value of P, Q, and alpha. Let's start with alpha. What's the most likely value of alpha? Yeah? 3/4, right? And you can, I'm just looking at the red, right? The red is the value of the 0th coin. How do I get the P, for example? P was coin 1. Yes? So I'm looking only at those examples, sequences that start with H, and in this case I have 3 of them.
So it's between 0.5 and 0.75.
And what do you mean between 0.5?
So in 2
Yeah, but I can tell it exactly, right? I'm looking at the first one, the third one, and the fourth one. And I'm counting how many H's are here among the 12, right? And that gives me my best estimate for P. So this is really labeled data, right? I gave you labeled data. You know these came from the P coin, this came from the Q coin, estimate. Yes?
Sorry, I think just to clarify, are you using that formula for heads toss coin 1, otherwise toss coin 2 for each? Or once you've tossed coin 0 and it tells you which coin to toss next, you're tossing that each time?
Each one of them is a separate experiment. So this is why I said the red is the value of coin 0. Okay? So this is coin 0, and then it came out ahead, so I use coin 1. This is again coin 0.
But you are using coin 1 for the rest.
Yeah, for the rest of those. Until you see red, it's the same coin. Okay? So again, in this experiment, you can think about it as labeled data, right? So you can estimate. Third scenario, kind of like before, toss coin 0, if head, toss coin 1, otherwise, toss coin 2. And here you observe just the blue. So this is from the first case to your question. This is from the first case, but I don't know what coin 0 came up with. This is from the second case. A different toss of coin 0, but I don't know which one, and so on. So I see what happens in each one of the experiments, but I don't see coin 0. And again, the question is, estimate the most likely values of P, Q, and alpha. So you can think about it this way. This is my generative model here. I first toss coin 0. As a function of coin 0, I'm tossing, and I'm getting the first toss, the second toss, the third toss. But I don't observe this. All I observe is this. So the question is, what do we do now? What do we do now? So this is the unlabeled case. And before you start guessing, I can tell you that there's no known analytical solution to this problem in the general case. So we don't know how to compute the value of the parameters in a way that maximizes the likelihood of the data in the general case. What we're going to do instead, we're going to run an iterative algorithm. And what is going to be known about this iterative algorithm is that every round of the iterative algorithm increases the likelihood of the data. And that does not mean that we converge to the maximum likelihood, but it does mean that we converge to a local maximum of the likelihood. Question?
Why couldn't you run some sort of clustering algorithm and say, like, especially if the sequences were longer, with 4 it's a little bit less useful. Let's say there's one cluster that clusters around 0.75 and one cluster that clusters around 0.5. And then that would be the most likely value for P and Q.
And that's kind of what I'm going to do. But this does not give me an analytical solution. It's true that had I known that there is some gap between the P and the Q, for example, I would be able to guarantee something. If I see these many examples and the gap between P and Q is at least this, then I will, with high probability, learn the right parameters or estimate the right parameters. But in general, we don't know how to do this.
But if there's no gap,
If the gap is small, you may need to see a lot of data. Yeah.
So once I have P and Q, once I've estimated P and Q, it's trivial to estimate alpha, right?
I don't know if it's trivial, but the same algorithm is gonna be used for that. In this case, I'm gonna estimate all 3 of them together. But clearly that knowing one of them is gonna make your life a little bit easier. You're gonna use the same algorithm, at least I think that you'll have to use the same algorithm. I don't think that there's going to be an analytical solution here. So what are we going to do? The intuition, I think, is the same intuition that you just expressed. So if we knew which of the data points came from coin 1 and which came from coin 2, there's no problem, right? This is a reduction to scenario 2 that we had before. Really what we're going to do is we're going to do this. The same thing that we've seen before, which is the simple maximum likelihood estimation under the Bernoulli assumption, right? Which we've done before. But we cannot do this. Instead, what are we going to do? We're going to use an iterative approach for estimating the parameters. Essentially, it's going to go like this. We're going to guess the probability that a given data point came from coin 1 or coin 2. Once we have this guess, we actually have a label, a fictional label, and weight according to this guess probability that we have. And this is now going to allow us to compute the most likely value of the parameters, as we've done with naive Bayes just earlier. Once we have parameters, we can compute the log likelihood of the data. Once we have the log likelihood of the data, we can estimate the parameters, the most likely parameters for this that will maximize the log likelihood of the data. So essentially what we play here is with this. If we know the labels, we can determine the model parameters. If we know the model parameters, we can predict the labels. So this is the left side of this equation here that I write. And this is going to depend on the likelihood of the data. So if I know an expression for the likelihood of the data, I can ask, okay, so what are the parameters that maximize this likelihood? So this is the game we're going to play. We're going to guess label that will give us model parameters. We're going to write an expression for the likelihood of the data, maximize it so that we can get the best model parameters. Okay, so let's try to do this explicitly. So again, we have alpha, p, and q. We're playing the same coin game as before. And for a minute, we're going to assume that someone gave us the parameters. So these are p hat, q hat, and alpha hat that we're given. So now that we have parameters, you can look at a toss or a sequence of coin tosses and say, what is the probability that this came from coin 1? You can just compute it. So that's what we're going to do, right? So again, my notation is going to be this. I'm going to assume n data point. In each case, we have m tosses and hi heads. So now that I have these guessed parameters, I can ask, what's the probability that the ith data point came from coin 1? Let's compute it. This is going to be called the expectation step, the E step of EM. So what is this probability? I'm going to denote it P1I, the probability that the ith point came from the first coin. And Bayes' rule says, okay, so P of coin 1 is the label, right? That the data was labeled coin 1 or came from coin 1 is P of di given coin 1 times P of coin 1 divided by P of d. That's it. And now we can compute it because we have parameters. We guessed alpha hat, p hat, q hat. So this is just P of coin 1 is alpha. P of the data, given that it's coin 1, means use the p's. So it's p to the h, 1 minus p to the a minus h. And here I'm normalizing. It's either alpha with the p's or 1 minus alpha with the q's. So that's my estimate of the label. Remember, this is what I call a fractional label. Now, every example has P1i, the probability that it came from 1, and it also has 1 minus this, if you want, which is the probability it came from the second. So now that I have this, I can compute the likelihood of the data. Now, if I have an expression for the likelihood of the data as a function of this PQ alpha, or P hat, Q hat, alpha hat, once I have this expression, I can find, okay, so what are the values, P hat, Q hat, alpha hat, that maximize this likelihood? And I can keep on going. That's going to be the idea. So the difficult part now is going to be to write the likelihood. We're going to maximize the log likelihood of the data, of the endpoints. And this is the expression that I'm writing for the log likelihood. It's the sum over all endpoints, log of the probability of D given PQ alpha. I already assumed that all the data points are independent, and I took the log. So instead of the product of the probabilities, now it's the sum of the log probabilities. Now, notice that I actually don't know how to compute it because one of the variables, the coin's name, is hidden. I don't see it. So what I'm going to do is I'm going to marginalize over it. So instead of writing log this probability, I'm going to write log sum. Y could be 0 or 1. In fact, should have been 1 or 2, given the names that I'm given before. So, but we'll carry 0, 1, 2 values. That's the important thing. P of di comma y, PQ alpha. Now the issue is that we have an algebra problem here. The sum is inside the log. You see log of sum over 2 values, and making this maximum likelihood solution difficult. We don't know how to solve this analytically. What we're going to do is we're going to make an assumption and actually bound the maximum likelihood. And this is where some algebra comes in, and we're going to show you the exact development, but basically wave my hands. It's more important for me that you understand the idea. So here is what we're going to do, and this is why it's called expectation maximization. Since the latent variable y is not observed, I can't really use the complete data log likelihood. I cannot do it exactly. Instead, I'm going to use the expectation of this log likelihood, expectation under the posterior distribution, P1i, as a way to approximate this log probability. Specifically, you can think about it, okay, so this log probability, think about it as a random variable. It depends on the value y of the coin. We don't know the value y of the coin, but we have the probability that this y is 1 or 0. So I'm going to compute the expectation relative to these probabilities, and this is what I'm going to maximize. Now, I'm writing the exact math here, and I'm going to go over it quickly, just that but you don't really need to understand this. So basically what I'm doing is I'm writing this explicitly here. So this is the log likelihood, the expression that we've just written. And this with the marginalization over 0, 1. And basically, how can I write it? So this is P of A, B, given something, right? That's what's written at the top. P of A, B typically is P of A given B times P of B. So that's what I'm writing here, right? So this is A, sorry, let's call this BA. P of BA, so it's P of B given A times P of A. Okay? I just did very simple thing. Now notice that what do I have now? I have a sum of this probability times P of Y given something. This is my posterior, right? What is the label? y is the label. So I can say that this is just the expectation according to the variable y of P of D given P alpha Q. So this is really just a notational thing. This expression is an expectation over y. And once I have this, I'm done. I'm using an inequality that says, you know, the log of the expectation is always greater than the expectation of the log. Why is this true? Again, you don't need to know, but this is a graph of log. It's a concave function, right? So if I take 2 points, this and this, and I take their average, the average is going to be below the function because the function is concave. So it goes like this. You see, the log of this point is larger than the average. And therefore, I can say that this is greater than this. This is called Jensen Inequality, and that's what I'm going to use here. But again, you can forget this and just skip to this step here. I'm maximizing the expectation of this random variable, and that's going to be good enough for us. So what am I doing? I'm doing this expected log likelihood. I've written this before. I'm just writing it again in exactly the same way. I just replace the order of E and sum. Now there's going to be a little bit more algebra that is written here. Oh, where is it? Here, that again you don't need to do to know. The important thing is that with this little bit algebra, you can write this. You can write the expression of the expected log likelihood as the sum of these two expressions that make a lot of sense. Is P1I the guess, the estimate that we have for the probability that this ith point came from 1 times log P of di n1 given the parameters plus 1 minus P1I times log P di0 given the parameters. And again, as I said, this is basically a little bit of algebra and playing with random variables, nothing sophisticated. I'm going to write this now explicitly for the coin. What did we say? I want to write down the expectation of log P data point given the parameters, first row. And this can be written as, it's not exactly this because I had to, in my algebra, I dropped a term that doesn't matter for the maximization. So I'm using this approximate equal here. It's the sum over I, P1I log P of 1 comma di given the parameters, plus 1 minus P1I log P0 d given the parameters. So basically, I split it to the two cases, if y is 1 or if y is 0. And now I can write it down. We've written this down before. I can write it down now. So it's P1I. What I get here is log alpha hat P to the h 1 minus P to the m minus h. And in the second case, P1I should have been 1 minus P1I here. Sorry. Log 1 minus alpha q to the h 1 minus q to the m minus h. That's it. So that's my expression. Now I'm taking log of this. So when I'm taking the log, I'm getting, again, the P1I is outside, log alpha, h log p, a minus h log 1 minus p, and the same here. So here it's correct. 1 minus p log 1 minus alpha, h log q, a minus h log 1 minus q. So it's really simple Bernoulli algebra. Yes?
So is the P1I referring to the probability that I am tossing coin 1?
No. P1I is what I computed before in my First step. P1i is this. It's, this is P1i. P1i is the probability that the ith data point came from coin 1. So think about it as the label of the data point. So it's exactly the same game as we played before. I show you the data point. Had you known P1i, you could estimate the P and the Q. How would you estimate the P and the Q? When I asked you before we did algebra, you said, oh, I'm going to look, if you're sure that this came from coin 1, and this came from coin 2, and this again came from coin 1, I'm going to look only on the coin 1, count how many H's are there, and use this to estimate, right? Basically divide this by the number of tosses. It's exactly the same thing, only that now it's fractional. So let's go back to this example here. Where is it? Up. No, I'm going to go to here. Let's look at this example. If I tell you that the first, the third, and the fourth came from coin 1, you know how to compute P. Everyone agrees? Basically, you're going to say, okay, let's forget this one for a second. We just care about these. There are 12 tosses, out of which 3, 6, 8 came from coin 1. It came out ahead, and therefore P is 8 over 12. Agreed? Now, let's relax it a little bit. I'm not telling you that this is coin 1, coin 2, coin 1, coin 1. Rather, I'm telling you the probability that this is from coin 1 is a half, a half, a half, a half. What will you do now? You're going to do the same thing. You're going to count. Okay, so let's concentrate on point 1. So these 3 heads really count as 3 over 2 heads. These 2 heads now count toward coin 1. They count as 1. So I have now 4 over 2. These 3 counts as 3 over 2 again. And these count again as 1 more. Okay? So basically you count all of them with the fraction. What is the fraction? This fraction is the P1i. How much do you believe that this came from coin 1? That's what I mean by fractional labels. Yes?
Shouldn't that correspond to the probability that coin 0 is head?
No, I told you that in the first case I told you coin 0 came out head. So I tossed coin 1. In the second case, I told you I couldn't really see exactly what came up, what coin 0 came up to. I think with probability 50%, I think it was head. So now you count this as 50% coin 1 and 50% coin 2. Or maybe your vision is even better. I'm 3/4 sure that coin 0 came head. So now you're going to count these as 3/4 toward coin 1 and 1/4 toward coin 2. And this one may be 1/4 towards coin 1 and 3/4 coin 2 and so on. So basically, the P1i is the label, but it doesn't have to be a 0-1 label. It could be a 3/4 label. And this is where it came from. So okay, basically, let's go back to this. So what I'm claiming is that you know how to run this algorithm. I tell you my estimate for P1i, which is my estimate for these red things. Even if it's a fractional estimate, you know how to estimate now the P and the Q. Agree with me? You just count fractions. All I'm doing now is I'm writing this explicitly. How do I write this explicitly? I started with assuming that my guess is the PQ alpha, the parameters of the model. I could have started directly with my estimate is this P1i, but this is a more kind of principled way to do it. Now that I have estimate for these, I have the label. I have an estimate for the label. And now I'm in the same situation that I was 2 slides ago, right? For each example, I have a label, a fractional label, and I'm going to count the h's and the t's to get p and q's. I'm just writing this explicitly, and writing this explicitly means first compute this P1i, now write the likelihood, which I've written here. I've written here the likelihood, the expected likelihood, and now I'm telling you, oh, you know what? It's exactly the same thing that you did in your head. You counted how many times did I get H, how many times did I get T, and you divided by the total number. I'm going to show you that this is really what you have to do. Once you have this as your likelihood, what is the best P, what is the best Q, and what is the best alpha? Just like we did a week ago, differentiate relative to alpha, P, and Q, and get the most likely value. So let's do it. I'm taking this expression. So I just want to make sure that you understand. All I've done here is what you've done in your head when we looked at this example. I'm just writing it. And now let's differentiate based on alpha. Look again. What happens to this guy when you differentiate based on alpha? This disappears, you get this, and you get this, right? These 2 parts, which means you get P1i over alpha minus 1 minus P1i over 1 minus alpha, sum over all examples, and you want this to be 0. If you do the algebra, which is very easy here, you get this. Make sense? Why does this make sense? What's the meaning of this?
Alpha is just the probability of the first part and having a head.
Yes, so if you want to make sure, let's assume that all the P1i's are either 0 or 1s. Okay? Extreme probabilities. So basically this means count how many examples were labeled 1 and divide by n. But in general, each example was a little bit labeled 1 and a little bit labeled 2. I'm counting how much was it labeled 1 and divide by n. So that would have been your guess when we played before with the HHHT. This is how you did it. And exactly the same thing, if I'm differentiating relative to P, just make sure that you understand that, the alpha is going to disappear, the Q's are going to disappear, you're going to get just the expression with the P's, which is going to give you this. So it's going to be sum over all examples, P1i, H over P, minus M minus H over 1 minus P. When you solve this and isolate P, you're going to get this. And again, think about this. It's a little bit more subtle than before, but makes a lot of sense, right? So it's the weighted by how much of the label says that it's coin 1 of H over M. Before we just said, let's assume it's all label 1, so we did H over M. Now I'm saying, okay, but only 3/4 of it, I'm sure that it's coin 1. A quarter could count toward coin 2, so I'm weighting this H over M by P1i, and I'm normalizing here. So it actually makes sense. So if you go to your 3 slides earlier and do this game, you will see that this is how you would have estimated it. All I've done here is I've ran the algorithm formally so that you can actually code it. So that's what we've done. So really a very simple algorithm. I'm summarizing it here again in a less simple way because we have to carry the notation with us. So what is the general EM procedure? We're going to run another example here in a few minutes, so it will further clarify it. So I'm guessing parameters. Let's call it theta 0. In the E step, I'm using the current parameters to find the posterior distribution of the latent variable. What does that mean? Guess the label. P of Z given the data and the old parameters. All right, this is my P1I. Guess the label. Once I guess the label, I'm computing the expectation of the log likelihood of the data, which is this long expression that I've written before under the Bernoulli thing. So once I have this expectation that often is written as Q, and this is my expression, sum over all possible values of the hidden variable, the label of the coin in this case, the probability of Z given X times log of X, the data, comma, label given the parameters. What I'm going to do is I'm going to compute the argmax of this. How do I compute the argmax? I'm differentiating relative to each one of the parameters and computing the maximum. If I only had 3 options for the parameters, I would just compute the value for each one of them and choose. But in general, because the parameters are continuous, I'm differentiating relative to each one of them and choosing the max. So this is a more obscure way to do what we've done here in a very explicit way, but this is the algorithm. Questions? Yeah.
Can you go back a slide? Yeah, so P1I, so like going back to the example of coin from 0, 1, so is P1I supposed to be like 0? Or is that actually like the coin 1? Because I thought the experiment was like you flip coin 0 and then you have like these coin 1 and coin 2 flips. And like it seems like here the P1I should be like P0I.
Okay, let's do this this way. Coin Z, coin 0, and coin 1. Oh, you don't see it. Okay. Up. So I changed the names of the coins. Z is the one at the top that decides the label, and then I have 0 and 1. So because Y, later on I wrote that Y changes from 0 to 1. So let's call the coins 0 or 1. And I'm going to change this in the rest of the notation. So the coins are 0 and 1, and the one that determines the label, I'm going to call it coin Z.
So it would be the P1I would become the PZI.
Yes.
Okay, cool.
Yes.
So the probability that a given sequence has a label, either coin 0 or coin 1, to calculate that, that's a P1I, right?
Yes. It's the label of the coin.
So to calculate that label, we take into account the probability that the first coin, that coin Z is heads, and the probability that we've observed.
Okay, just 1 second. So let's do 2 things here. Let's just think about this step, which is the easy step. In this case, you gave me the parameters of the model, the P, Q, and alpha. And now I looked at a sequence of M tosses, and you asked me what is the probability that this sequence of M tosses came from this coin? Right? There are 2 options. It could either it's either the 0th coin or the first coin that generated it. Okay? What is the probability that it's this coin? I know that this coin has a probability P for head, and the other one has Q for head. So this is the probability. It's alpha, right? Because I'm going to use this coin here if the Z coin came up head, and this happens with probability alpha, times P to the H, 1 minus P to the M minus H, normalized.
So the alpha is P of coin 1, and the
Now the alpha is coin Z, right? I changed the names to coin Z. So alpha is the coin at the head, the one that decides which coin I'm going to use later. If this coin came up head, I'm going to use one of the coins, the P coin. Otherwise, I'm going to use the Q coin. So the question is, once you observe the M tosses, you want to estimate where is it coming from. So I'm claiming that the probability of where is it coming from, where is the probability that the ith data point, came from 1, which is the P coin, is, this is just Bayes' rule, P of coin 1, given that I observe the ith data point, is P of D given coin 1, P of coin 1, P of D. Now the probability that it's coin 1 is alpha. Okay, because the coin at the top is going to give me head with probability alpha, and then I'm going to use the P coin in this case. So P of coin 1 is alpha. P of the data given coin 1 is P to the H, 1 minus P to the M minus H. Okay, everyone agrees with that? And then I normalized. So that gives me the guess for the label. Once I have the guess for the label, I can look at all my data and say, okay, so I've seen n examples. This is the probability or the likelihood of observing this data given that PQ alpha are my parameters. And I'm just writing this down. And I wrote this down here. Up, one back. This is the probability or the expected probability that what I've seen are these n data points. M data points with each one of them is labeled P1I. That is, it's labeled as coming from the P coin with probability P1I. And each one of them had H heads out of the M tosses. That's the probability of observing this data. And now I'm asking, okay, so if that's the probability of observing the data, what is the most likely value of the M, of the PQ alpha to have generated it? It's exactly the same question as, here is a coin, it came from the same, here is a sequence of tosses, it came from the same coin. What's the probability of this coin to produce a head? What you did is you counted, and you counted how many heads out of the total number of tosses and divided. It's exactly the same thing that I'm doing here with the fractions. Yes?
I just want to clarify that when you're referring to DI, you said it's the data, so like in the...
DI is the ith data point. So in the game that I had before, it's these 4 tosses, the HHTH that I showed you. That's the ith data point.
Okay. So in that case, I would go between like 1 and 4 or something?
In that case, it was 4. Yes. So each one of these is a data point. There are 4 data points. Okay? Okay, so that's EM. And the real thing that you have to convince yourself of is that this would have been the algorithm that you would run yourself, or that you ran yourself when we played these 4 data points. So let's move on to take another example. And the other example is going to be, summary. It's a general procedure, so I can run this for Bernoulli. I can run it for other algorithm, other probability distribution, as I'll just show. Really, it depends on assuming a family of probability distribution. So it's a family of algorithms. Often in the literature, they'll tell you we use DM. They will forget to tell you what was the probability distribution. Sometimes they will, sometimes they will not. Now, it's a very good algorithm, and I want to attend to it a little bit later today still, if you got the family of distribution right. If you didn't, perhaps not so good. Okay, so what I want to do now is I want to do k-means. Anyone knows what is k-mean clustering? Anyone can describe k-means clustering?
We just saw this in marketing. So you have data points, and the idea here is that you're going to pick centroid, which is like one point, and then check the distance from all the points to that specific point. You can do this with many different centroids. So you can do 1, 2, 3, 4, to whatever you want. And the idea here is that you want to classify the points based on that distance. So check the optimal distance for that centroid that you pick such that it minimizes all the distance and then classify the points according to it.
Yeah. So do you want another version?
Well, I was just going to say, like, you have to move your centroids according to.
Yeah.
Right. So you have to do first you want to choose k, which is how many clusters will I have. Let's assume we chose k at 7. Then you choose 7 centroids, and you take all the points and place them with their centroids. So each point is going to choose a centroid that it wants to be with based on its distance from the centroid. Now you have 7 groups of data. Once you have these groups of data, you re-estimate what is the centroid. And now you have 7 new centroids. Now you forget where the points were, and you ask each point again, which centroid you want to be with. And they position themselves next to the centroid. Again, you have 7 data sets. And you keep on doing it. Once you have 7 data sets, each one of them estimates its centroid. You drop the points from the groups and split again. This is k-means algorithm, and in fact, this is a version of EM that we're going to talk about now. The difference is going to be, and I'm giving you a glimpse into the future, that in your algorithm, and the way I describe your algorithm, the assignment of a point to a centroid, or the assignment of a point to its cluster, was a hard assignment. The point decided which centroid it's going to be with, and that's it. In EM, this is going to be fractional. Remember the labels from before? A point is going to say, well, I'm 0.8 with centroid number 1, 0.1 with centroid number 2, 0.05 with centroid number 3, and so on. And when you compute the new centroid, now you cannot just count how many points like centroid wide, you have to do it fractionally. Because part of this point likes centroid 1, but part of it likes centroid 2, and so on. So you have to do weighted decision, just like what we've done before. So that's going to be k-means. It's a clustering algorithm. You see a lot of data points. Someone told you they came from 2 Gaussians, and the question that you want to ask is, where is it coming from? Or how do I decide for each point which Gaussian is it coming from, and what is the mean centroid of this Gaussian? So just to remind you, this is k-means. This is a normal distribution. The probability of x given mu, the mean, is written this way. I'm going to assume now that I have this m data points. and the log likelihood of the data, therefore, is the sum over these m data points of this. And it's easy to see that, therefore, maximizing the log likelihood is just like minimizing this, right? So I'm just basically taking the log. So basically, what does that mean? That in normal distribution, the mean is the number mu that minimizes the sum of these distances. What is the solution for this guy? Which, can you analytically tell me what is the mu that minimizes these L2 distances from all data points? Summation divided by n, or average. So magically, this is a complex expression, right? This says, well, I'm going to look for a mu such that for all data points, I'm going to compute xi minus mu, square it, and sum it for all the data points. And I'm going to find the mu that is the smallest. So I'm going to try a lot of mu's and see which one gives me the lowest value. It turns out, thanks to simple calculus, that this turns out to be the average. Magic. It's exactly the same thing as the m over k that we've done with Bernoulli. Right? Really the same idea. So now I'm going to generalize this problem. I don't have just one Gaussian with one mu, but rather I'm going to have multiple Gaussians, which we're going to call a mixture of Gaussian, and they are going to have multiple mu, mu1, mu_j, up to mu_m, and the question is going to be, how do I decide each point which mu it belongs to, and what are the mu's? What are the best mu's for this? So I'm going to assume, to simplify things, that I have m Gaussians. They will all have the same standard deviation, and they will only be different by the mu's. So again, I'm asking the same question that I asked before. Assume that we observe the data. I'm sitting on one data point, xi. What is the probability that it came from the distribution mu_j? It's the P1i from before. So Pij, the probability that the ith data point came from the jth Gaussian, is this. Bayes rule. It's Pxi given mu_j. Oh, let's start here. The probability that xi is labeled mu_j, or came from the jth Gaussian, is P of xi given mu_j, P of mu_j divided by P of xi. Bayes rule. I'm assuming uniform distribution among the mu_j's, so P of mu_j is just going to be 1 over k. Okay? I have k clusters, and therefore what I have now is P of x given xi, given mu is mu_j, normalized. The 1 over k is going to disappear, and what I'm going to get is this expression for the normal distribution. Okay? Okay, so notation. I'm going to invent k variables, one for each data point. I'm going to call them, for each data point, I'm going to invent k variables. That's the right way to say it. zi1 up to zik, such that zij is 1 if and only if f came from the jth distribution. Okay? So this is just a convention. It's going to be easy to use. So for each data point, k variable, notice that in real life, one of them is going to be 1, the others are going to be 0. So these are indicator variables that tell me where is this data point coming from. Notice also that if I compute the expectation of this random variable zij, it's going to be 1 times the probability that xi came from uj, plus 0 times the probability that it was not sampled from uj, and therefore this is exactly Pij that I had in the previous slide. So E, the expectation of this Zij, is just the probability the data point I came from J. Now with this, I can run EM and get the following k-means algorithm. So my parameters here, which I'm denoting H now, are the sigma and the k-mus, and I'm computing P of y given the hidden variables, which is exactly as saying P of x and the z's given H. This is just substituting the Gaussian formula. And notice what I'm writing here. So I don't know where is x coming from. So I'm writing it this way. I'm writing it Zij times xi minus mu aj squared. Now, one of them is going to be 1. The rest are going to be 0. So essentially, it's a compact way of writing sum over j, xi minus mu j for the right one. Okay? I didn't know which is the right one, so that's why I invented these Zijs. Okay? So now that I have this way of representing it, I can compute the likelihood given the observed data, the M examples here. Where is it? These M examples. And it's just this way. It's the log of P of y given H, sum over all M examples of this expression that I've written above. I'm replacing, I'm now taking the expectation of this, expectation of what I had before, and I change the order between the expectation of the sum, just as we did before. Expectation is linear, so expectation of sum is the sum of the expectation. So nothing sophisticated. And what do I get now? So now I got this expression, which I copied from the previous slide. The likelihood of the parameters given the previous parameters is this expression. And what I'm going to do is I'm going to differentiate with respect to each one of the parameters. If you differentiate with respect to each one of the parameters, this guy here is going to disappear. And what you're going to get is sum of E Zij times x minus mu j. And I want this to be 0. There is some constant that comes from the power here and from these guys here, which I fold into this C. So what did I do? Again, I started with these Pijs, the probability that this data point came from J. Now I computed the likelihood of this data. I got this expression, which I differentiated relative to the mu's. And when I differentiate, that's what I get. And again, let's think about what does that mean. This is, let's assume that the EZAJs are just 0 and 1 for a second. Okay? So if they are 0 and 1, what you're saying here is mu j is going to be the number of points that belong to the J's cluster divided by the total number of points, which is what you expected to happen. Okay, so that gives me an algorithm, right? So what is my algorithm? I'm going to guess initial parameters. Based on these initial parameters, I'm going to guess labels. I'm going to tell you for each data point which j it belongs to, Pij. In your algorithm before, I actually physically guessed it. I said, you're cluster 1, you're cluster 2, you're cluster 3. Here, I'm not doing this in a hard way. I'm basically just saying the probability of you being in 1 is 0.5, the probability of you being in 2 is 0.3, the probability of you being in 3 is 0.1, and so on. So it's fractional. Once I have this fraction, as a function of writing the data, I can compute the new centroids. How do I compute the new centroids? I'm asking each point to choose a centroid, which is basically what's written here. And it's choosing it in a weighted way, because it's saying I'm counting myself a little bit toward this, a little bit for this, a little bit for this, which is written here with the weights of my point, the weight of xi toward the j's centroid is E of zij or Pij. Same thing. So it's a relaxation, if you want, of the hard k-means, and this is the real k-means. It's an EM algorithm. Okay, I ran through this a little bit quickly, and I want to leave you with, not with a summary, but with a question that I want to attend to next time. I was hoping to attend to it today, but here's a puzzle for you. Training a sample of data points. These are the data points, x0 up to xn. So it's n plus 1 dimensions, okay? N plus 1 vectors. And the task is to predict the value of x0, given that in the future I'm going to give you x1 up to xn. Okay? Again, training data, a bunch of n plus 1 tuples. Test data, a bunch of n tuples, x1 up to xn. My question for you is, how do you do it? So it's an applied machine learning question. Okay? Here's data, solve it. So we're going to revisit this at the beginning of Tuesday and recap also EM. So think about whether you have additional questions on what we've done today, because the end was a little bit fast. Okay? Have a good weekend. Hi.
Just have a couple quick questions about the lecture. Actually, just one question about the lecture. So I'm still kind of confused about the P1I. Maybe it's my bad.
Okay. Well, what is so?
So my issue is it different to predict the probability that this sequence is coming from coin 1 if I see the actual sequence or not? Because isn't predicting whether a given sequence...
Oh, you have to see it in order to compute P1I. If you see the expression that I wrote for P1I, it depends on how many H's and how many T's were there.
Okay. But is it not just the probability that coin 0 was ahead?
I don't know that. No, it's not.
It's not.
It's not. Think about it.
Because I've seen the sequence.
Yeah. So, I see. I think I see your confusion now.
I was trying to make it clear, but
You see, you don't know. You know the probability for the zero coin, the Z coin,
yeah,
to be zero, to be head or tail.
it's alpha.
So you know what's the probability that now I'm choosing coin 1 to generate this sequence.
Yeah.
But this is just my prior. Now that I see data generated, I know better.
I know better.
Because think about it. Think about very extreme P and Q. Okay? So P is 0.95 probability of head and Q is 0.01. Now, I'm not sure if this is a P sequence or a Q sequence because say alpha is 0.5. Right?
Yeah.
So I don't know what came out in alpha. I just know from the alpha toss. I just know what is the value of alpha. So it could be a P coin, a P sequence, could be a Q sequence.
But now that I've seen this...
Now that you see a lot of heads, you say, oh, this must be a P.
Okay.
Right? Okay. You see, so just knowing alpha is just a prior. It's not telling you which one it is, because unless it was deterministic, it doesn't tell you what to do. You see, so think about the extreme case, and it will clarify to you that looking at the data actually is going to do much better than just taking the prior.
Okay, I think I got that.
Okay, it's a good. Now I understand. I probably before I didn't understand what was your question.
I was trying to say, like, I'm estimating this P1I given the prior and the actual distribution.
Yeah. I understand your problem now, but I didn't understand it before. But it's clear to you.
Yeah, it is.
Okay, good.
Also, just one thing, I emailed you today before lecture about my homework too that I discussed with you before, after last lecture.
Okay. So I will forward it to them and they will check. So you described it. So you actually submitted,
on ENIAC and forgot to submit on
but you
Canvas.
submitted everything, including the PDF. Okay.
And really double check my files.
No. If you submitted it there, it should be there, I assume. And they'll be able to check.
Okay, I was just starting to get worried because it's a little bit late and I haven't approached this in time.
No. Of course, you should have done it earlier, but they will check.
Okay, thank you very much.
Sure. Yeah.
If I have, I have a data set of, 400,000, well, it's sort of like a black box data set. All I know is that it has 90 features and 400,000 data points.
Okay.
And I need to train, a neural network to optimize it.
So it's labeled data.
Yeah, it's labeled data. I have 400,000 labeled data points.
How many labels?
All of them are labeled.
How many different labels?
Well, it's a continuous problem. So it's like predicting the year. I know it's audio data.
Okay.
It's like predicting the year. How do I know how many layers to add? Or how many, well, more layers means it'll overfit more, right? So if I have a, and how do I know how much dropout to add?
You don't. So what I suggest that you do is you look at your performance on the training data too.
Yeah.
So you split it to train and test,
Yeah,
or
that's
it's
what I've
given.
done. I have,
So look at the gap between your performance on train
and then
performance
just if you're
on test.
overfitting, and then if you're overfitting, add more dropout.
Yeah.
Okay.
So what kind of numbers do you get with your initial architecture?
Well, this is my initial architecture right now. So I have one model, which is just 4 layers, 2 hidden layers, and then I'm getting a loss of around 5 years. So I predict something, I'm generally 5 years off.
Okay, but the loss is not necessarily giving you something. So how do you evaluate this?
My evaluation right now is, okay, so I have I'm doing mean squared error, but I also normalize the labels. I read up that something
So just a second, mean square error, so it's year,
yeah, and I predict a year.
and you want to know how far you
How
are
far
from
away
the
from the
year. Something that bothers me here is, how did you tell your model that these are years? That order matters? I'm not sure I understand the model here.
Well, if I just have one output, right, and I just try to optimize
So the output
that.
is a real value?
Yeah, the output is real valued, and I just try to
Okay,
optimize that,
okay,
then I'll
that-
eventually
that's
get
fine.
closer to that
Yeah.
output.
So you basically penalize it based on distance
away, yeah.
from the year.
Yeah.
Okay, and you get,
And then when I normalize it again, so I normalize all the labels.
okay, that doesn't matter. So it will be between 0 and 1.
Yeah, and now I'm getting 0.31 training loss and 0.79 validation loss. And this is only on a subset of the data. But yeah, I'm overfitting, and I have a pretty simple model. All I have is 2 hidden layers,
But you have a lot of data.
but I have a lot of data. So should I just have a more complex model, create a more complex model, and then
Try to cut the data by half and see what happens.
so less data?
I mean, that's a cheaper experiment. How long does it take you to train it?
It doesn't take that long because I'm using a Google cloud server. So right now I'm only training on 50,000 data points, and it takes 3 or 4 minutes to run 50 epochs.
Okay, so that's not bad.
It's not that bad.
Yeah, I think you should try both the data size
And
and the architecture.
Okay. Okay, I'll do
Because maybe the problem is easy.
Yeah. And like you don't need that many data points?
Yeah.
Okay.
So maybe you generalize after half the data point or quarter of the data point
Yeah.
already.
Okay, cool. Thank
Yeah.
you.
There's really no way to know